this is 4.3. We look at the homogeneous linear with the differential equations with the constant coefficient. So for the second order, be in the form of a times y double prime plus b times y prime plus c times y equals 0. Remember, homogeneous, so the right hand side is 0. Okay, so we're going to find the solution for this particular case. So this case, a, b, and c are real number, are constant. Use that term. So that's why it's called that way. So a, b, and c. A cannot be 0 because we are looking at the second order. Otherwise, no second order again. And they call the educated guess of the solution y equals e to the mx. Why we have to think about that form? Because the exponential, when you find the derivative, e to the mx, y prime, m e to the mx, y double prime, another m, right? M times m e to the mx, which is m to the second e to the mx. So it still remain e to the mx as the factor of the derivative for every time that you keep going. The thing that changed just the coefficient, or the real number. Okay, so that's why are you still there? You guys still with me?
Yep.
Okay, somehow the screen went away. I don't want to talk to myself. Okay, anyway, so from the solution, so that's the educated guess, because the pattern of the solution, every time you find the derivative, it will give you maybe the same or different constant as a coefficient, but the main part, which is the exponential, still the same. That's because the solution has to satisfy this differential equation. You see, they have, when you plug it in, it has to satisfy the y double prime, y prime, and y with the coefficient as a constant term. So from this kind of this guess of the solution, y equals e to the mx, we claim it satisfies the solution. That means the left-hand side of the equation equals the right-hand side of the equation. So the a as a coefficient times y double prime, which is m squared e to the mx, the b times the y prime, which is m e to the mx, and then c is, c multiplied by e to the mx equals 0. All of them have the factor e to the mx. So take e to the mx out. Now we have a m squared plus bm plus c equals 0. The left equals 0. That means each factor must be 0. But the restriction or the nature of exponential, it never be 0. Exponential graph, either increasing or decreasing, it never touch 0 unless you have the transformation. But this time we are talking about the basic exponential function. If exponential is not 0, it's forced am squared plus bm plus c to be 0. That's how we can find the solution m, okay? When you look at this equation, am squared plus bm plus c, look at the coefficient of each order. A here, b, c, and c. The order 2, power 2, order 1, power 1, order 0, that means the original y, okay, the original y, that is m to the power 0. So it's mapping one by one. The thing that my students in the past got lost all the time, the last term, just think about the order of the derivative. The original y, that means the order is 0. If you don't do the derivative, that means that is the same as original y. So the last term going to be just a constant c, or whatever the coefficient of the y term in the differential equation. So the point is to find the solution y equals e to the mx. To get to that, we have to know m. And what is m? That's the way to find m. by setting up the auxiliary equation. I have a hard time pronouncing that term. So auxiliary characteristic equation must be easier. Some textbook they use characteristic equation. Same thing, they are the same thing, but I use the ZIL textbook. So based on ZIL, they call auxiliary equation. Okay, you're gonna form the auxiliary equation from the homogeneous equation am squared plus bm plus c equals 0, which is a quadratic equation for the second order. If you have the third order, you're gonna have power 3 and so forth. The power depends on the order. So to find the solution m, quadratic formula is a generic way to find it. Otherwise, you can think about factoring. If factor works, go ahead. If not, quadratic formula always works. Okay, so negative, oh, where did it go? Where did it go? Again. There you go. So negative b, m is negative b. It keeps going back. Negative b plus minus square root of b squared minus 4ac all divided by 2a. That's easy, right? Yep, just from algebra class. All right, next one. So I already have more new slide open up. Okay, so from the examples, I gave you like different ones for different cases, and the higher order apply the same way. Before we do the order, let's wrap up one more time. For the solution of am squared plus bm plus c equals 0 from the quadratic formula, m equals negative b plus minus square root of b squared minus 4ac divided by 2a. The b squared minus 4ac, this is discriminant. Why is called discriminant? Because it distinguishes 3 different types of solution. Depends on this term give positive number, 0 or negative number. That's why you have 3 different cases. When you take the square root of positive, you get the positive number or the real root, right? The real number. If you take square root of 0, you get 0. That means you have repeated roots. So going to be repeated. And when you have to take the square root of negative, you're going to get imaginary number or the complex number. So that's why it's called discriminant. So for each case, for case 1, so you have the discriminant here. Let's use the term D. For D is greater than 0. So you have M1 not equal to M2 or 2 distinct real roots. For D equals 0, M1 equals M2 is called repeated roots. And for D less than 0, you have M1 and M2 as the conjugate complex. And the notation for the 0, they use the alpha plus minus beta I. Okay, alpha plus minus beta I. Or A plus minus BI, either one. I prefer A and B, but it doesn't matter. Anyway, one is the real part, the other one is the imaginary part. And how do you form the solution? For case number 1, the solution, okay, for case number, this is case 1, and then this is case number 2, and this is case number 3. So 3 different cases. For case 1, if you have different real roots, so gonna be y1 equals c1 e to the m1x, and y2 equals c2, not the c, sorry, wrong one. When we put them together, we put the c. So the fundamental set of solution, y1 is e to the m1x, and y2 is e to the m2x. And for case 2, y1 is e to the m1x. And since y1 and y2 are linearly independent, so y2 we can obtain using the reduction of order, that what we just did in 4.2, to have like x times e to the m1x. Okay, that's the reduction of order proof that the second solution will have the x multiplied to the known solution. And for case number 3, so y1 and let's see, the solution, I should write in the combination form. For the solution of the second one, it's kind of 2 different pieces, but you can write it as hang on, too many arrows. Let's see. Before I get to the last case, let me go back to case 1 and case 2. When you have like 2 individual solutions, you put them as y equals c1 e to the m1x plus c2 e to the m2x. And for the second case, we have y equals c1 e to the m1x plus c2 x times e to the m1x, where m1 and m2 are the same. For the case number 3, when you broke it as 2 different pieces, you have to use Euler technique or Euler formula to bring them back together in the same solution form. So y1, oh not y1, so the y or the general solution, y as c1 y1 plus c2 y2. After you use the Euler formula to simplify, to clean up the terms, I can help you during the office hours to show how to get to the finished form here. So the finished form of the solution in case 3 will be y equals e to the real part, which is alpha, times x multiplied by c1 cosine the imaginary part of the b times x plus c2 sine beta x. So you use the real part as a power of the e times x, and then the beta or the imaginary part would be part of the argument of the sine cosine.